I'm an entrepreneur and I'm a backer of entrepreneurs, and we've been at the forefront of some of the great scientific advances of our time. And many of them were enabled by Professor Kleinwerk's work. So when I was thinking about this 50th celebration, I thought it provided a great opportunity to highlight some unsung heroes and some of the scientific advances that they brought to market and brought to light. It's the story of light amplification by the stimulated emission of radiation. It began 100 years ago when Albert Einstein published his thoughts on the quantum theory of radiation, how matter and light interact. Specifically, he was expanding on his dialogue with Max Planck on how atoms emit light. It was part of a thought process that later on with Schrödinger and Heisenberg was codified as quantum mechanics, quantum theory. And there's a professor at NTT, physicist, named Soichi Sudo, that said quantum mechanics is the greatest, most successful theory yet devised by the human mind. So I'm going to give you one example of how that success manifested itself for all of our benefit. Einstein explained in this article on the quantum theory of radiation the mechanisms for two forms of emission. One, the spontaneous emission of light that comes in sort of a chaotic manner. It's the light you'll see from the sun with many, many different frequencies. In the second type of emission, he realized something that is astonishing because it does not exist anywhere in nature. It is something truly new under the sun, and that is how light could be created by the stimulated emission. It's an entirely man-made conception, and it's basically the relationship that he understood, that a photon going into an excited atom could, under certain circumstances, perfect conditions, knock the electron out of the excited state, knock it back down to its resting state, and in the process, that would emit a second photon. So basically one photon in, two photons out of exactly the same frequency, wavelength, and direction. The formula, of course, that we all know, E equals mc squared, sort of captures this phenomenon, c being the speed of light. Now, if all that sounds a little complicated, even Einstein was perplexed by this. Here's his quote. He said, "For the rest of my life, I will reflect on what light is." It took a lot of reflecting to glean some value out of this insight, something practical. In fact, it took 40 years before someone figured out how to make stimulated light. That someone was a Columbia University student named Gordon Gould. He was a hard-drinking, two-pack-a-day smoker with Marxist leanings. And let me describe to you what happened on November 13th, 1957. Here's a quote from Nick Taylor's great book that I'm sure none of you have read, but I recommend that you do. The insight, when it came, struck Gould with the force of a revelation. It was a Saturday night. He sat up in bed, marveling at its perfection. Like all good solutions, it was simple and obvious once you had the thought about it. It had been there all along, waiting to be seen for what it was. That night, Gordon Gould invented the laser. The laser is an acronym for light amplification by the stimulated emission of radiation. Remember those two words. 2 years later, in 1959, 10 years before the connection between UCLA and Stanford that Professor Kleinwerk just mentioned, Gould filed a patent on the light amplification by stimulated emission. It was entitled Optically Pumped Laser Amplifier. He owed a lot to his professors, so be nice to your professors. One of his professors, Charles Towns, subsequently won the Nobel Prize, and another one was Isidore Rabi, who had already had the Nobel Prize. And Rabi basically told him to start working on optical pumping, and so Gordon Gould was doing the very first optical pumping experiments in the United States of America. And it was kind of funny because at the first optical pumping conference, one of his rivals, who was pushing something called the optical maser, was introducing Gould, and he said, "Well, if we put optical maser in, put the O in place of the A, the laser of Gordon Gould's would be a loser." For decades, it was a loser for Gordon Gould because he'd gotten some bad information from one of his professors, and he was told that he had to have a working prototype before he could file a patent. So he left Columbia and applied to ARPA for funding for the project. ARPA is the same source that Leonard got when he was starting the ARPANET. But in this case, Gould's communist ties came back to haunt him, and the U.S. government refused to let him work on his own invention. And that delay allowed his rival, Thomas Maiman, at Hughes Research Labs. But Maiman had a problem. He had picked ruby crystal to be the source of the emissions, but he didn't have a power source that was strong enough or the right wavelengths to stimulate this emission that he conceptually knew was happening. And this is where the UCLA graduate came in. Charles Asawa was born to Japanese immigrants. He became the man of his family at the age of 13 because his father died and his older brother drowned. And during World War II, he and his family were sent to a relocation camp in Arkansas. They let him out of the relocation camp so he could join the Army. And he was one of 400 translators that was sent over to help rebuild Japan after when General Douglas MacArthur went over after the war. When all that was done, he came back to UCLA and he got his master's degree in spectroscopy. And after that was done, he went to work for this gentleman, Thomas Maiman, at Hughes. When he heard about this struggle that Maiman had in terms of getting the power source to pump out these photons, he had an idea. And so Asawa suggested a photographic flash lamp from a professional camera as the source of the energy. It looked exactly like this. They curled this around the ruby, and the damn thing worked. On May 16th, 1960, they set off the flash, and the first laser produced 10,000 watts of power for a millionth of a second, and this is what it looked like. Ruby crystal, a quartz flash cube, and he had created something totally new under the sun. Something not found anywhere in nature, at least on this Earth. There's some discussion that there may be lasing in quasars deep in space. But meanwhile, on the other side of the country, Gordon Gould had the fight of his life on his hands. Basically, it was the beginning of a 30-year battle that Gordon started to get credit for inventing the laser and to get the patents issued on the laser. Fascinating story. The book I referred to earlier, Nick Taylor's book, is called Laser. Now, to pay for his expenses during these years of litigation, Gordon co-founded a company called Optelecom. It was an optical telecommunications company, obviously, to turn amplification into products. And for the first contract, he hooked up a video sensor to a fiber optic cable, called it a rocket on a string, the string being fiber optics. And that was the first project they had. This was 1972. Corning Glass had just demonstrated low-loss fiber clear enough to convey a signal by a laser over meaningful long distances, but they couldn't produce it for several years after that. So Gordon and his handful of merry people were forced to spin their own fiber. And so they had hydrogen tanks, torches in the basement of one of his employees. Well, the guy's kids slept upstairs. So you do what you got to do. He was trying to take advantage of one of the unique things about light. Light obviously is as fast as anything goes in the universe, but it's also immortal. If you can set off a photon in space, it will literally travel to the end of time. In fact, when you go out of this room, if you go out of this room, you'll be bombarded by photons that were literally created at the beginning of the universe. People don't realize that photons have been coming since the beginning of time. And so that immortality is a feature that Gordon was trying to preserve, but he had a problem because those early fibers, and even to this day, fiber glass is not purely fiber glass. It has impurities, metal, sometimes water. And so he had to figure out a way to restore the immortality to these fading lights, and he was doing that by harnessing light amplification. To work on this project and others, he hired this fellow who just earned a PhD from Brigham Young University, named David Huber. Beat a path to the East Coast because he wanted to work with Gordon Gould and Telecom. And soon enough, they were producing a lot of products that relied on the interaction between light and matter, such as lasers and optical amplification systems and wave mixing. That idea of wave mixing, Bell Labs was also working on, and it evolved into wave division multiplexing, or WDM. WDM is the ability to put data on slightly different frequencies of light that can be sent down a fiber at exactly the same time without any interference. Now, separate and apart from these optical networks was sort of the Kleinrock-inspired computer networks that were proliferating in academia and government and some corporations, while the optical amplification techniques were being adopted primarily by telecommunications company. First one, not too far from here, actually, GTE installed an optical system in the late 70s. AT&T, MCI, and Sprint in the mid-'80s, and late 80s, the National Science Foundation had a big backbone that was privatized in 1993. And that privatization and the convergence of some of the things that were happening because of what your professor did was putting a lot of pressure on the backbone networks. Now, this is where I had the pleasure and privilege of coming onto the scene at this moment. When Telecom CEO introduced me to this guy, and I jumped in right away. This was a few weeks after the World Wide Web had just been released. There were only 70 web servers in the world. Early days. Anybody want to guess how many web servers there are today? I have no idea. I have no idea, but it's a lot more than 70. And it happened to be 36 years to the day from when Gordon Gould had that proverbial revelation at night that Dr. Huber and I and Telecom issued the founder's shares and chartered a new company named Ciena Corporation to use optical amplification to try to free up all 99.9% of the capacity, potential transmission capacity of fiber that was latent. And stretching out for that goal, we delivered optical amplification on steroids. We called it the paradigm shift in communications, and we promised to our investors that it was going to permit full utilization of the data superhighway. We didn't even talk about it as the internet back then. It's pretty funny. Anyway, that was we delivered a 16-channel, 40 gigabits per second system. It was deployed on the Sprint network that at that time was the largest carrier of internet traffic. Now, maybe that doesn't sound exciting to you, but WDM really did change communications forever by multiplying the capacity of optical networks, the backbone that carries all the data that we use every day. WDM literally made global what Kleinrock made possible. After we succeeded with this launch, George Gilder, is a tech guru, saw the optical amplifier that sort of powered this, and he compared it in importance to the integrated circuit. Why did he say that? Well, the integrated circuit, of course, powers all of our computers and our phones. The optical amplifier powers the communication revolution. And it encouraged the fellow I mentioned earlier, Soshi Sudo, to predict that the optical amplifier would usher in a worldwide revolution called the information age. That was in '97. Well, their premonitions proved spot on because our 16-channel WDM system was just the beginning. Further advances led to 100-channel, and then 1,000-channel, and then far more thanks to a lot of advances in fiber quality, semiconductor processing, and huge advances in a lot of the optical technologies from competitors like Alcatel, Cisco, Infinera, and Lucent. Now, I wanted to show you a timeline. This is from Forbes magazine, the sort of bits per second, so you can kind of put this all in perspective. Over here on the far left, from your standpoint, is 1844, the telegraph, 8 bits per second coming out of a telegraph line. If you fast forward over to 1983, sort of where the first fibers were being deployed, per line, 45 million bits per second. And then 14 years later, when, I'll read it to you, Ciena promises to deliver 100 gigabit fiber optic equipment. It was 100 billion bits per second by 1997. The full extent of that capacity utilization has been breathtaking. In fact, it's incomprehensible. Let me give you a very recent example of where we are. In 2018 on Telstra's Melbourne, Australia system, Ericsson and Telstra installed a 30.4 trillion bit per second over a twisted pair. Now, that's equal to 1.2 million 4K high definition video per second. That's optical amplification. With the convergence of optical and computing networks and the obsolescence over time of the copper telecom infrastructure, the WDM has become the common basis of all regional, metro, national, international, and oceanic telecommunication systems in the world. In fact, the fellow that wrote this book and said that, confirmed this last week, as much as 99% of all IP traffic travels through optically amplified WDM systems. So, in summary, because optical amplification perpetuates the immortality of light-based packets, light wins. And what does that mean for each of us, each of you? It means that we live a lot of our lives on light. It's not something we think about, but every minute, trillions and trillions of immortalized photons are flashed at a speed that's incomprehensible. A millionth of a billionth of the blink of a flash of an eye is what these lasers and optical amplifiers are flashing at. And that's what's carrying all this information that we share and we search. It's coming over these networks. It just, it's astonishing to me to think about everything we do online, much of what we do on our mobile devices and our phones goes up to a tower, down to a fiber optic network, and it's blasted on little photons of light. Just think about what that means. Little bits of discrete energy that Einstein figured out how to pull out of an atom, and here we are. Anyway, like Einstein, you can reflect all you want on that. It's still a mind blower. Okay, in conclusion, one astonishing thought from one of our greatest thinkers led to the laser and the light amplifier. It came from a communist sympathizer in New York and his rival in California, assisted by a UCLA graduate. And what followed was 6 decades of innovation and planetary scale deployments that became the infrastructure of the 21st century. My firm, Spencer Trask, is always looking for big thinkers and big ideas. We're inspired by Mr. Spencer Trask, who funded the development of the original light bulb, the incandescent light from Thomas Edison. And then he ran the first electricity system in the world, which is in New York. And so he helped really, in a way, light up the 20th century. I like to think that the work that we just talked about, the laser and the optical amplification systems, are lighting up the 21st century and the internet. And if there's one thing I've learned, it's that you never know where a great idea is going to come from. I know that there are some really great minds in this school. So I'd like you to keep your eyes out for the next person, the next great mind, the next big idea, maybe sitting in a classroom or a lab right next to you. So keep your eyes out for me. I will definitely be keeping my eyes on UCLA. Thank you very much.